I made a worksheet you can fill out as you watch this video, plus practice problems for this unit, and AP Calculus practice tests to help you get ready for the AP test. So click the link in the description to check those out. In Unit 2, we learned about derivative rules like power, product, and quotient rule, and we will use those heavily here in Unit 3. We also learned how to take the derivatives of trig, log, and exponential functions. What we learn here about implicit differentiation is going to be absolutely critical for solving related rates problems in Unit 4. We're also going to learn about chain rule in this unit, and we'll be using that constantly throughout the entire rest of the course, but especially in Unit 6, which is where we learn how to undo the chain rule when we integrate. Even though this is a short unit, it's really critical that we remember both chain rule and implicit differentiation because even though they're a little tough, they do get used all the time on the AP test. Remember that chain rule gives us a way to differentiate composite functions, and a composite function is just a function of another function. So these are all composite functions because we have the function x cubed plus 2x nested inside of the sine function, the exponential function, and this power function. And remember that chain rule tells us that when we want to differentiate a composite function like one of these, we apply it in 2 steps. First, we take the derivative of the outside function, ignoring the inside function. So if we apply this first step to these 3 functions, here's what that looks like. The derivative of this first sine function, we take the derivative of the outside. Well, the derivative of sine is cosine. So we get cosine, and now here we ignore the inside function. So we ignore x cubed plus 2x. That's step 1 of the chain rule for this first function. For the second function, we know that the derivative of an exponential will just be that same exponential function. So differentiating the outside, we still just get e to the x cubed plus 2x. In other words, we just ignore the exponent for now, because that's our inside function. For the third function, when we take the derivative, we address the power function. So we have 3, then the inside function raised to the power of 2. So we treat it as a power function, we bring the 2 down in front, so we get 6, and for now we'll ignore that inside function. 2 minus 1 in the exponent gives us 1, no need to write an exponent of 1. That's step 1 of the chain rule. Step 2 of the chain rule tells us that we then have to multiply by the derivative of what's inside. That inside function for all 3 of these is x cubed plus 2x, so we multiply by that derivative. Well, the derivative of x cubed plus 2x is 3x squared plus 2, which means that we then take each of these functions and we multiply by 3x squared plus 2. So that's step 2 of the chain rule for the trig function. Here we multiply by 3x squared plus 2, and here we multiply by 3x squared plus 2, and now we have each of our 3 derivatives, we just need to simplify. As long as we remember these 2 steps with chain rule, we'll be able to apply it to any function that's a composite function. And then the last thing we want to remember with chain rule is that we'll often have to apply it with other derivative rules. This, for example, is a rational function, which means we'll need to apply quotient rule to take its derivative. But you can see we have all of these composite functions nested within the numerator and denominator, so we'll have to use chain rule and quotient rule together, plus product rule and power rule, in order to take its derivative. And when you have something complicated like this, the best thing to do is to build an outline first and then take the derivative of each piece separately. So instead of trying to go through this in order and potentially risk getting lost and disorganized, losing your place in the derivative, just go ahead and build an outline. We'll say that the derivative is f prime of x is equal to, we know this is quotient rule, and quotient rule looks like this. We take the derivative of the numerator multiplied by the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. We know that's going to be our outline for this rational function. Then let's build each of these pieces separately. So here, away from the derivative function, what you want to do is find the derivative of the numerator itself, the derivative of the denominator, and then if you wanted to, you could also find the denominator squared, since we'll need that here for our quotient rule formula. Find these pieces separately, and then plug them into your derivative function. Obviously, when we take each piece separately, the numerator is obvious. We just take the entire numerator here from the original function. The denominator is obvious. We just take the denominator. The denominator squared is easy. When we take the denominator here and we square it, instead of raising this to the power of 2, we'll get this to the power of 4. So we'll get 3x to the 4th minus 6x plus 2 all raised to the power of 4. And then all that we're left with is the derivative of the denominator and the derivative of the numerator. So we can focus in on each of those pieces, find them somewhere away from this formula. Once we have every piece calculated individually, then we can go ahead and plug it back into our derivative function. So when it comes to implicitly defined functions, we want to distinguish between x and y variables. So when it comes to x variables, we want to differentiate those like normal, like we always have. So in Unit 2, we learned all about derivative rules. We did power rule, product rule, quotient rule, and we always were differentiating x like a variable, and we want to continue doing that. Nothing changes about how we treat x when we take a derivative. But we're going to start differentiating y. And when we differentiate y, when we take the derivative of y, we're going to first differentiate it just like we would x. We're going to sort of treat it like a variable, just like we would take the derivative of x, we're going to take the derivative of y. However, after we do that, we then need to multiply by y prime or dy over dx because y is a function of x, which means we have to apply chain rule to take its derivative. So, for example, if you come across in a function 3x squared, you recognize you need to use power rule, you take the derivative, and the derivative there is 6x. When you come across 3y squared, you want to take its derivative. Well, you treat y first exactly like you would x, so the derivative is 6y. However, then you have to apply this blue piece. Because you just differentiated y, you now need to multiply either by y prime, and so your derivative is 6y y prime, or you could write it this way. You could say 6y and then multiply by dy over dx. One more example. You come across sine of x squared. You want to take the derivative, you do that like normal. You take the derivative using chain rule and you say cosine of x squared, but then we have to multiply by 2x because that's the derivative of the inside function. So there's our chain rule application. There's your derivative. But if we want to find the derivative of sine of y squared, then we first treat y just like we would x, and we say, okay, the derivative is cosine of y squared, and then we multiply by the inside function, 2y, and so we've accomplished this first part. We've differentiated just like we would x. However, then we apply the blue part. Once that first part's done, we have to multiply by y prime or by dy over dx. So let's just say we chose dy over dx, and there is our derivative of sine of y squared. So always remember those two parts. Let's look at one example really quickly to make the point also that all of our other derivative rules still apply. So when we have a function like this one, we can work straight from left to right through both sides of the equation. We always have to remember to differentiate both sides of the equation. But let's start with this 3x squared e to the y. Well, we have to use product rule here because we have two functions. We have 3x squared and we have e to the y. So if we set up product rule, we'll set up an outline here. We know product rule, our outline is going to look like this. So the derivative here, we'll take the derivative of 3x squared. That's just like normal, that's 6x. Then according to product rule, we just multiply by the other function, so e to the y. We didn't differentiate this part with the y in it, so we don't have to multiply by y prime or by dy over dx. But then we calculate the other half of our product rule formula. This time we leave 3x squared alone, so 3x squared, but then we have to differentiate e to the y. This is the first time we're differentiating a y. Well, we treat y exactly as we would x, so the derivative of e to the y is e to the y, but then we have to multiply by y prime or dy over dx because we just took the derivative of something with y in it. So we multiply by dy over dx. This second part here, minus 2y over ln of x, well, we could do this with quotient rule, or we could separate the y out from the fraction and do it with product rule. Let's go ahead and do it with quotient rule. So let's go ahead and build a quotient rule outline. We know we'll have the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, all divided by the denominator squared. There's our quotient rule outline. And now let's go ahead and apply quotient rule. So here we take the derivative of the numerator. Well, that's just going to be 2, but then we have to multiply by dy over dx, multiplied by the denominator minus the numerator, 2y, times the derivative of the denominator. Well, the derivative of ln of x is 1 over x. And then we have the denominator squared. So ln of x squared, we can simplify from there. And then, of course, the last thing we always have to remember is on the right-hand side, we have a constant, but we still have to differentiate that. The derivative of a constant is always 0, so we need to make sure we get that 0 on the right side. And then be really careful here. Remember, our goal is to simplify this as much as possible and solve for dy over dx. Well, when we solve this for dy over dx, here's what we're going to get. The thing I want to point out here is that we have to be really careful about signs on our dy over dx function. And that's because on the AP test, a lot of times they'll flip around the signs in the answer to give you an expression that's equivalent to the one you found, but looks a little different because of the way they've switched around the signs. For example, you can see here in our numerator, we've got 2 negative signs. Both terms are negative. What they might do is take these negative signs, factor out the negative, and instead put that in front of the fraction. So they put the negative sign out in front here, turn this into a positive and this into a positive. Or they may take these 2 terms here and swap them, reordering the terms. And they could even go into the denominator here and swap these terms around, factor out a negative sign, and change around the way that this answer looks. It's going to be an equivalent expression. They're just changing around the signs. So you have to be really careful. You may get the correct answer, but you may have to manipulate it a little bit to match it up to the correct answer on the AP exam. So for topic 3.3, differentiating inverse functions, there's really 2 kinds of problems that show up most often on the AP test, and we really want to be able to handle both of them. The first thing we want to remember is that when we're dealing with inverse functions, remember, are just reflections of each other over the line y equals x, and they just have their x and y values swapped. So here in this graph, we have the function y equals x cubed in purple, and we have the function x equals y cubed in dark blue. We have only swapped the places of the x and y variables in those 2 functions, and you can see the result here in the graph. They look like perfect mirror images of each other over this line y equals x. So just remember, they have the variables swapped, you change the places of all the x and y variables, and they're reflections of each other over the line y equals x. So what you'll often be asked to do is start with a function that looks normal, and let's go ahead and take this x cubed function, and you'll be asked to find its inverse function, but evaluated at a particular point. So let's say evaluated at 2. So we need to find the inverse function evaluated at x equals 2. So in order to do that, all we're going to do is follow a simple set of steps. So we're going to remember that we can write f of x as y. So we're just going to say y equals x cubed instead of f of x. We're going to swap x and y variables. So we're going to say x equals y cubed instead. Then we're going to solve for y. And the way that we're going to do that is by taking the cube root of both sides. So we're going to say x to the 1/3 is equal to y cubed and then raised to the 1/3 power. The reason we do that is to cancel the exponent on the y, because 3 times 1/3 is 1. We get y to the first over on the right-hand side. So we're going to get x to the 1/3 is equal to y, or we can rewrite that as y equals x to the 1/3. And then in the same way that we changed f of x into y, we can change y back into, so we'll rewrite this as the inverse function is equal to x to the 1/3. Now that we have the inverse function, we just need to find this value by evaluating at x equals 2. So the value then that we want to find, we'll say the inverse function at 2 is equal to, we plug 2 into the function here, we get 2 to the 1/3, and it means we have the cube root of 2. We could leave it that way. We could write it as the cube root of 2, and that's our answer for that kind of problem. The other kind of problem that we'll commonly be given is we'll be told that f and g are both differentiable functions and they're inverses of one another. And knowing that they're inverses of one another, we have some information about them. Let's say, for instance, we know g of 1 is 9. We know that, let's say, f prime of 9 is 2. And we've been asked to find g prime of 1. Let's say that's the problem we've been given. Knowing that f and g are inverses of each other, here's how we solve that. We'll go ahead and draw some coordinate axes, and then we can start labeling some points. So we have the two functions f and g. We don't know what they look like, but we know some points on each function. So here we have g of 1 equals 9. So that means that when x is 1, g is going to give us 9. So we can plot this point here, 1, 9, and let's just go ahead and put a g next to that so we know that that relates to g. Because f and g are inverses of each other, we know that there's a point on f that just has these values flipped. So if 1, 9 is on g, the curve of g, then 9, 1 is on the curve of f. So we can come over here and say 9, 1 is maybe right about here. We'll call this 9, 1, and we'll say that that relates to f. So we've addressed this piece of information. What about this piece? F prime of 9 is 2. Well, what that's saying is that the derivative of the function f at 9 is equal to 2, or the slope of the function at 9 is equal to 2. So if we imagine a slope of roughly 2, that's going to look something like this. The slope through this point, at that point, might look something like that. That's what that piece of information is telling us. Now we know that if these functions are inverses of one another, then the slopes at these points also have to be inverses. And we can kind of picture what that looks like. Here at 1, 9, the slope would look something roughly like this, because remember, we have reflections of the curve over the line y equals x. If we call that the line y equals x, we have to have symmetry over this line. So that's roughly what the slope should look like. But in order to calculate that, all we have to realize here is that if the slope over here is 2, so the slope at this point here is 2, then the slope of the function g at that corresponding point has to be the reciprocal. So instead of 2, we literally just take the reciprocal, and the slope at g has to be 1/2. So the slope over here has to be 1/2, and that's what we've been asked for, is the slope of g when x is equal to 1. And so this has to be equal to 1/2, because 1/2 is the reciprocal of the slope of the function f at that corresponding point over the line. We could also go ahead and write in here our other piece of information we found, that f of 9 is equal to 1, and those are now our 4 corresponding pieces of information. G of 1 equals 9 is the corresponding piece of information to f of 9 equals 1, and these reciprocal slopes are corresponding pieces of information at these 2 corresponding points. Now for inverse trig functions, and remember those are these functions here, we'll also see these written as y equals arcsine of x, arccosine of x, arctan, arccosecant, arcsecant, arccotangent. So those are equivalent notations, but for these inverse trig functions, we're going to need to know the formulas for their derivatives. And I really would recommend memorizing these formulas if at all possible, because you're going to be pressed for time on the AP exam, and you don't want to be you don't want to be generating these formulas, building these formulas yourself, even though you can do that. If you have them memorized, you can move quickly and not spend time coming up with these yourself. So I would recommend memorizing these formulas. And then there's really only 2 key things we need to remember about applying these to find inverse trig derivatives. The first thing is to choose the correct x. So let's say, for instance, that instead of being given y equals inverse cosecant of x, we're instead given y equals inverse cosecant of 3x squared. Well, remember, this formula is based on having x as the argument of the inverse cosecant function. Well, here our argument is 3x squared, not x, which means that in these 2 spots here, for this x and this x, we need to use 3x squared instead of the x. So the first thing to remember is to always pick the correct x, or use the correct x. So we know that the derivative here then is going to be -1 divided by, and then instead of absolute value of x, absolute value of 3x squared. And then instead of square root of x squared minus 1, we're going to get square root of 3x squared quantity squared minus 1. And then we can simplify this expression for our derivative. That's the derivative. So number 1, pick the correct x. Number 2, if the argument is anything other than x, like it is here, we have 3x squared instead of just x, we need to apply chain rule and multiply by the derivative of that inside function. So the derivative of 3x squared is 6x, which means that this is actually not our derivative function. We have to multiply here by 6x, and now this is actually our correct derivative function. So the two key things you want to watch out for are use the correct x, whichever x you're given here, you want to put that into the formula everywhere where you have an x. And then the second thing is to multiply by the derivative of what's inside. If you have any argument other than x, you go ahead and apply chain rule and you multiply by the derivative of that inside function. Topic 3.5 is all about figuring out which derivative rules we're going to need to apply to take the derivative of a particular function. So let's say we start with this one as an example. There's two key things that we want to take away from this topic. First is figuring out what derivative rules you need to use, and then second is kind of figuring out the order in which you need to use them. And if we start with the order in which we need to use them, you always want to work from the outside of the function toward the inside of the function. So in this particular case, we wouldn't start by focusing on, let's say, this 9x squared, which is buried deep inside the function. We would instead step back, we would take a look at what we have here, and we would say, oh, this is a fraction, it's a rational function. Therefore, my first derivative rule, my primary derivative rule, is of course going to be quotient rule, because I have a quotient here. So this is my primary derivative. I'm working from the outside, I'm starting from the outside, and overall, my function here is a quotient. Then I work toward the inside and I say, okay, what else am I going to need? Well, I say I have secant of x, so I know I'm going to need the trig rule, the trig derivative of the secant function. I can see in the denominator I have a product. I have 9x squared plus 2 multiplied by the other function, e to the 4x. I have the product of two functions. So I know I'm going to need product rule as well when I deal with that denominator. Of course, I'm going to need power rule. I can see, for example, I have this 9x squared here. So I know I'm going to need power rule. And I have e to the 4x with this 4x nested inside of the exponential function. That's a composite, so I know I'm going to need chain rule as well. So the idea here is just to be able to look quickly at a function, think through all of the derivative rules you might use, but most importantly, focus on working from the outside toward the inside to figure out what your primary rule is. What this means is that when I take the derivative of this function, I'm going to build an outline for the quotient rule, and then all these other rules are going to get applied inside of that quotient rule derivative. If, on the other hand, we wrap this function in parentheses and we raise it to the second power, like this, now my primary rule is instead the power rule, because this is a power function. I've got this thing nested inside here, but essentially I have something raised to the power of 2. That's a power function, so power rule is going to be my overriding rule, and then inside of that, I'm going to start nesting in quotient rule and the rule for the derivative of secant and product rule and chain rule. So always work from the outside toward the inside, and maybe make a list ahead of time before you start a problem like this of the rules that you know you're going to use in order to take the derivative. Okay, so talking about higher order derivatives, which are going to be your second derivatives, third derivatives, fourth derivatives, but primarily we're dealing with second derivatives. Remember that the second derivative is just the derivative of the first derivative. The second derivative is the derivative of the first derivative. So if you're given a function y, then the first derivative you might write as y prime, and the second derivative you might write as y double prime. Or if you're given a function, let's call it f of x, and you find the first derivative, you're going to write that as f prime of x, and then of course your second derivative is going to be f double prime of x, and you're just differentiating each time. So the second derivative is the derivative of the first derivative. And on the AP test, they'll often talk about twice differentiable functions. You'll see this in questions a twice differentiable function, and that just means that not only is the original function defined, but the first derivative and the second derivative are also defined. So a twice differentiable function means that all three of these are defined functions. Of course, you take the second derivative using all the same derivative rules that you would have used on the first derivative, you just differentiate again. When it comes to implicit functions, implicitly defined functions, let's say, for instance, we've been given this function as the original function. Its first derivative is this here, dy over dx. We already found the first derivative. Then we went and differentiated this and found the second derivative. So this is the second derivative of this original implicitly defined function. The thing you have to remember here when you're differentiating an implicitly defined function is that in the second derivative, you're going to end up with these values here for dy dx or y prime, depending on how you write it. But this first derivative, these indicate here the first derivative. So what you need to do is take your first derivative function that you found and remember to plug it in to any spot where you have that first derivative nested inside of your second derivative. So once you find the second derivative, your last step will be to plug this first derivative into those spots and then simplify the second derivative as much as you can when you're dealing with an implicitly defined function like this one. Okay, so that's it for Unit 3. You really want to make sure that you know how to use chain rule to differentiate composite functions and apply chain rule alongside other derivative rules like power product and quotient rule. You want to be able to differentiate inverse and implicit functions, and you want to know how to find higher order derivatives, both for explicitly defined functions and for implicitly defined functions. Once you're good to go on Unit 3, make sure to come back and move on to Unit 4, where we'll dig into applications of differentiation.